The continuation of the electrode kinetics, we have started the discussion of implication of the current potential characteristics, in which we have discussed in previous lecture the exchange current, and now we are going to discuss the current over potential equation. In previous lectures we have derived this equation which is showing the current measured using the type of circuit shown here, where the system is using two electrode setup, in which voltage is the applied potential, and here the current is measured. So the measured current is given by the equation given here as the equation number 1. We can have 3 electrode or 4 electrode system depending on the assembly of the cell, but here we are concerned about the effect of applied voltage and the measured current. So here in equation 1, this relation is very important, because this one, or the variation derived from this equation number 1, is used in the treatment of every problem requiring an amount of heterogeneous kinetics. So here K0 is known as the standard rate constant or the heterogeneous constant, which show the rate of electron or the charge transfer at the electrode and solution interface, and this is simply the kinetic facility of a redox couple. So here we can see that in equation 1, the electrode kinetics or the measured current is proportional to the concentration of the oxidized or reduced species of electrolyte at the surface of electrode. So in previous lecture we have optimized the condition while saying that there is an equilibrium between the oxidized and reduced species at the bulk and the electrode surface. So at this condition, the cathodic component and anodic component are equal, resulting overall current equal to 0, in which we have converted the concentrations to bulk concentration, which are important for this condition, and any component, either cathodic or anodic component, is known as the exchange current. So equation 1 gives the measurement of current at the surface of the electrode, which is the generalized equation, and it is depending on the concentration of the oxidized and reduced species, and it is combining the cathodic and anodic components. So this current is actually the difference of two types of currents, whereas the exchange current is actually the either component that is either cathodic or anodic when the overall current is 0, and these two components are contributing equally. Here we can see that the current, that is the total current produced or generated with application of the either positive or negative potential, is proportional to the standard rate constant, and as well as the exchange current is also proportional to the standard rate constant. In today's discussion, we will see that working with the I naught, that is the exchange current, will be described in terms of the deviation from the equilibrium potential, that is known as the over potential. So here we are going to discuss the description of the exchange current in terms of over potential. Over potential is the simple potential which require more energy than the thermodynamically expected to derive the simple redox reaction, as given here. So potential is the energy required to convert this oxidized form to reduced form, but experimentally there is an extra amount of potential is required to carry out this reaction, which is higher than the value required that is measured theoretically. So this our potential is represented as eta. So in later discussion we will replace the equilibrium standard electrode potential with this overpotential. We have two equations for the current. So first one is the total current and the second one is the exchange current. So by dividing the equation 1 with equation 2, we can derive the relation between the exchange current and the potential that will be replaced with the overpotential. So here we have cancelled the common terms for two equations and simplify the ratio of current over the exchange current. Now I'm going to extract the common terms in these two different components. So here we can see that the C naught over CR with alpha term is common for this component, and for this one we have C naught star over CR star raised to power minus 1 minus alpha is common. So here we can see that I have divided C naught star term raised to power 1 with this concentration term, and this factor is as it is, and here C naught star is minus alpha, so we can write as C naught star as positive term, and this one is as it is. Similarly, the term second component have been rearranged as shown here. So this equation is equation number 3. So now again consider equation number 1, which is showing the total current measured. So if the total current is 0 when the concentration at the electrode surface is in equilibrium with the bulk concentration, and the E is equal to E equilibrium, and here E naught star is the standard electrode potential at equilibrium condition.